Let me just get started with functions, the definitions. Most of the audience already know what a function is, and I put some definitions there. This is an example of something that is not here on the board, a function. Yeah, it is not a function because for two reasons. One of them is that every element in the domain has to have an image, and the image or the outputs of each one of the elements in the domain has to be single. We cannot have this situation where there is two. We're going to be considering functions that are onto, which means everybody in the codomain is going to have a pre-image, and one-to-one, which means we cannot have repetitions. This is not even a function, so that doesn't even count as one-to-one, but these are the kinds of examples we're going to be looking at. A set in which, again, for every element in the domain, there's one element in the codomain, and the other way around is true. For every element here, there's only a single one on the left that maps into those elements. This is another example. Same sets, same elements, a different example, a different function that is one-to-one and onto. So once we establish a one-to-one and onto function from one set to another, there may be more than one. In this case, there are six possible ways to put a one-to-one and onto relationship between those two sets. Although I'm not going to be talking about the number of ways we can do that. This is not one-to-one, and it is not onto, because clearly the X is not covered. Everybody here has to be covered. And it may not happen that we have the two elements going to the same output. So that is not one-to-one and onto. Okay. Is it possible to have a one-to-one and onto from that set S to this set U? By the way, you can ask any questions or interrupt. I might do this a little interactively. What do you think? Is it possible? Please answer.
Does each element you have to have a corresponding input?
Correct. And it has to be unique. So can we have a one-to-one and onto relationship between those two sets? And the answer is no, we can't. Yes?
Is one-to-one and onto the same thing? What are the two differences? What is?
One-to-one and onto means this. If every element over there corresponds to a single element over here and vice versa, we're done. That's one-to-one and onto. It's fairly straightforward in the sense that there is no possibilities for having one element with two over there, two pre-images, and nothing can be left out. Everything has to be filled in.
I guess what's the difference between onto and one-to-one?
If the set did not have the X, then it would be onto. Everybody's covered.
Oh.
And if the set, and if C was going to X, then we would have a one-to-one. Yeah. So one-to-one and onto means they're almost the same set. Well, almost, not. From a cardinality point of view, they are the same. Quite often we have more than one set that we are connecting with one-to-one and onto functions. If this is the case, for instance, S goes to T, T goes to V, it isn't too difficult to put together a relationship between S and V. Again, if we have two, we can make one going from S to V because we just bypass the elements in T. Yeah, so we can put together different one-to-one and onto relationships to establish relationships between two sets that are farther apart. We're going to do this, by the way, in this talk, towards the end of the talk. Yeah. How many elements, how many circles do you see?
10.
Oh, that was quick. Yeah, it is 10. And you probably did something like that. We use one-to-one and onto functions often. Every time you count, you are actually doing a one-to-one and onto function, establishing a one-to-one and onto function. You are very familiar with the set from 1 to 10, and then you just establish the relationship. Oh, this is the number 1, that's the number 2, and so forth. By the way, there's over 3 million ways to do that. Remember, there's several ways to establish a one-to-one and onto relationship. All we need is one, though. Once you count them once, that's it. You don't need to count them again. Well, unless you want to double check, but you don't need to count them again. Once you establish one-to-one and onto relationship, that's it. We know the two sets are equivalent. That's kind of what we do quite often. We count the elements here, we count the elements there, and we say, oh, they are of the sets are of the same cardinality, same size. Yeah.
What is n sub 3? Is that just a random variable?
No, it's just my way of stating the set 1, 2, and 3 that contains 1, 2, and 3. So n sub 4 would be 1, 2, 3, 4. So that was n sub 10. Yeah. And I don't even know if that is a standard notation. I just came up with that. Now, with infinite sets, weird things start happening. You can start having one-to-one and onto relationships between sets and subsets of the same set. And initially, the way I'm thinking of this is pretend you have the same set. Okay, so 1, 1, 2, 2, 3, 3, 4, 4. 1 going to 1, 2 going to 2. This is pretty clear that we have a one-to-one and onto relationship with, of a set with itself. If we take 1 away, can we still have a one-to-one and onto relationship? And the answer is yes. We have to do some shifting, some moving around. 1 cannot go to 1 because 1 is gone. So I'm going to set 1 to go to 2. But now 2 cannot go to 2 anymore because the function wouldn't be 1 to 1. So 2 has to go somewhere else. And we can tell 2 to go to 3. But then this 3 cannot go to that 3 anymore. So we shift the numbers, as this diagram shows. Yeah, 6 goes to 7. Now, when we establish a one-to-one and onto relationship, we want to make sure we know the precise formula for the element. So if I tell you, where does 1,000 go? Can you tell me where the 1,000 is going to go? Exactly. And vice versa. If I tell you 1,000 on the other set, you know it is going to come back to 999. Knowing precisely where elements go or come from is crucial, is important. Well, I'm making it an important issue. I take that back. Sometimes it is important, but I'm thinking of it as important for this particular talk. So now we're going to do that with the interval from 0 to 1. By the way, this is the interval of all the numbers, including 0 and including 1. Up here, we have all the numbers between 0 and 1, excluding 0, though. And we want to establish a one-to-one and onto relationship between those two sets. Now, remember, we were able to do that here by shifting. How am I going to shift here? Taking elements from 1, and it doesn't matter. Once you have a one-to-one relationship, it doesn't quite matter too much which one is the domain and which one is the codomain, because they are sort of equivalent. Let me think which way I did it. Yeah, well, let's just show the diagram. Here's the actual formula that I'm going to be using to establish a one-to-one and onto relationship between those two sets. If an element, Here it is. We're going from the closed set to the semi-open set. That's how we're defining this function L. So we're going from here up to there. And I have to establish precisely how we're going to do this. Whoops, the other way. If x has this kind of form, 1 minus a reciprocal of a power of 2, then we're going to send it to a different reciprocal, well, 1 minus a reciprocal of a power of 2, a different one. And if x does not have that form, then just leave it alone. That's the way we're going to map the closed interval 0, 1 into the semi-open interval or semi-closed interval 0, 1. This is kind of hard to picture just with the formula, but this is the precise formula. Here's the picture. So this is what we're going to do. Oh, I inverted them. Yeah. So this is 0, 1, including 0 and including 1. 0, 1, excluding 0, including 1. So this guy has to go somewhere. Just like with the 1 has to go somewhere once the 1 is gone. And that's what I'm doing. I'm taking the same set and from that set, taking this point off. So to establish a one-to-one and onto relationship, I have to decide where this guy is going to go, and I'm going to send it to a half. But then the half cannot go to 1/2 because that is already taken. So 1/2 has to go somewhere else. Well, we're going to send it to 3/4. OK, but 3/4 is gone. 3/4 cannot go to 3/4. So 3/4 has to go to 7/8, and so forth. So I can precisely tell you where every element from this set is going to here. And by the way, this is not a unique way of doing this. There's many, many, many possibilities. Yeah. Another one that I actually kind of wanted to do because it's easier to think of is to send 1/2 to 1/4. I would have to work with these numbers. 1/4 to 1/8. 1/8 to 1/16. That's much simpler to think of. However, the lines were going to cross, so that's why I didn't do that. Yeah, but yeah. Anyway, this is just one way of mapping a closed interval into a semi-open interval. So far, so good? Does that make sense? OK, let's look at a different example. This is just another example that I like to bring up. A lot of people like to bring up. Consider the set of natural numbers, 1, 2, 3, 4, and so forth, and this set of pairs of natural numbers, such as 1, 1, 1, 2, 1, 3, and so forth, 3, 4, 5, 7, all the pairs of natural numbers, ordered pairs of natural numbers. Here's a diagram of the two of them. There is 1, 2, 3, and so forth. By the way, this is a partial picture of the set. This line actually continues forever on the right, 10, 11, 12, and so forth. This is a partial picture of the grid of points. The picture actually continues on here, 10, 1, 11, 1, and so forth, in all different directions. Well, actually, right, up, right. And the question is it possible to put them in one-to-one and onto relationship? Notice that in this case, we're not only hiding one element. Well, let me back up a little bit. Notice that this set is embedded into this set because this point could correspond to this point down here. The second point could correspond to this point, and so forth. So it's like this line is already there, and then we are producing many, many, many other lines on top of that. So the question is, can we put them into a one-to-one and onto relationship? And the answer is yes. This is well known. The answer is yes. And this is the way we do it. We can assign this guy with 1. We can call this the first point, second, third, fourth point, fifth, sixth, 7, 8, 9, 10, 11, 12, and so forth. We can go in diagonals and start assigning to each element on the grid a number in the natural number set. I've seen this half a dozen times over the years. But nobody has shown me an actual function. For instance, what is the 100th term? What pair corresponds to 100? Or vice versa, if you have 2020, what is that element? Is that the 17th, the 80th element? What is it? Well, here's the formula. If you give me a number, say 1,000, let's work with 1,000. If you give me 1,000, I can find the precise x and y value that correspond to 1,000. We can tell in this listing of the points which one will be the 1,000th. I mean, I can tell this is the 13th, this is the 14th element for 2, and so forth. But what about the 1,000th? Oops, the other way. Let's find the 1,000th element. I can show you how to. Nancy, will you be so kind to please do the square root of 2,000? Or Megan, either one.
We're double checking.
And then subtract 0.5.
Square root of 2,000, subtract 0.5.
After the square root, yep. And we want only the integer portion of that. What did you get? 44. OK, we're not done yet. So that's just so 44. And then, again, the square root of 2,000 at 0.5, and then only the integer portion of that.
45.
OK, thank you. Let's multiply them together. The 44 and the 45. Yeah, because I'm using the brackets for the greatest integer that is less than or equal to. So only the 44 and the 45 is what we need.
1,980.
Let's divide by 2, please.
Divide by 2. 990.
Oh, so, and then we do 1,000 minus 990. That is 10. So the x value is 10. And what about the y value? This is the formula. Let's see. So this was 44. This was 45. I kind of remember, I think this was 990, wasn't it?
Yes.
990.
Multiply together, divide by 2. Yes, 990.
And now we need to do this, which is going to be, if I'm not mistaken, 46.
Megan already said.
What is it?
So you had 990 plus the square root of 2,000 plus 1.5.
Well, the integer portion.
1036.
I'm sorry? Minus 1,000 after we do that.
Gotcha. So minus 1,036.
Oh, it's just 36?
After the minus 1,000.
Oh, OK, thank you. So, sorry to make this a little long, but so the point I want to make is that we can precisely tell that the 1,000th element is 10, comma 36. Am I making sense? Yeah. If you go 10 back in this diagram, 10 this way, and then 36 up, that's the 1,000th element. Now, when we have a one-to-one and onto function, we have to be able to do this precisely, as we just did. Tell exactly where everything goes. And when we have a one-to-one and onto function, we have to be able to go back. So if you have the 10, comma 36 element, is it true that it is going to give us back the 1,000th point on the grid? We don't have to. Well, perhaps, yeah, we should check that. Yeah. So pretend x, 10, 36, Oh, thank you. So it does give us 1,000. So those three formulas, well, this is technically speaking 1 because we're going from m to the pair xy to the vector, perhaps, xy. And then we're going back from the vector back to the m. And this establishes a one-to-one and onto function. Now, if we want to be completely formal, we, in addition to this, have to establish that the composition of the functions actually gives us identities. I'm not going to do that with this. But that's formally what we have to do to really, really establish that those functions are one-to-one and onto. Now, these formulas are not very, they're easy to use. You guys use them on your calculators, but they're geometrically nice. But as far as being able to actually show that the composition give identities is not, the formulas we're using are not friendly. We might have to come up with a different map. Yeah. This is just an example of the precision we kind of need, the formulas, to really establish a one-to-one and onto function. Okay. Now let's change gears a little bit. Let's talk about infinite decimals. Numbers that look like this, we're going to consider numbers that look like this: 0, point, 1 digit, second digit, third digit, and so forth. For instance, this one is such a number. Infinite decimals, if there is an infinite number of non-zero digits, we're going to call those numbers, those kind of numbers, infinite decimals, if they don't stop. By stopping, what I mean is that we don't start with zeros and only zeros. So if they don't stop, if they go on forever, then we call this an infinite decimal. That's the way we're going to call this. This is an example of an infinite decimal. And we're going to use some other names. For instance, I'm going to call this kind of decimal a decimal with a tail of 8s. So if there's 8s, if there's one point after which there is only 8s, we're going to say that this decimal has a tail of 8s. If a decimal has a tail of zeros, then we're going to call the decimal exact decimal. So for instance, 0.25 is an exact decimal because after a little while, there's just zeros. And we usually just rewrite the 0.25 this way. 0.333. And then when you stop, that is exact. However, 0.3333 on forever means we don't stop putting 3's, and consequently, we have an infinite decimal. Yeah, this is not exact. That is exact. Yeah. Now, decimal representations are tricky. This is one of the complications with establishing a one-to-one and onto function in general. Numbers may have more than one representation. Remember back here when we had a lot of precision? There is no ambiguity. Once you know x and y, you can certainly figure out m. There's no ifs, or there's no square root where you can find a plus or minus, nothing. It's very clear. It's very this formula is very deterministic. However, with decimals, we have a problem. Some numbers have more than one representation. For instance, 0.25 may be expressed as 0.2499999 forever. And the first thing we have to do is clamp the numbers down and think of only one representation if we're going to work with this kind of numbers, especially infinite decimals. This is your classic proof that 0.9999 is actually equal to 1. Multiply by 10, which moves the decimal point over 1, and we have 9 point, the same tail of 9s. If we subtract this number minus this number, on the left side of the equations, we end up with 9x. This number minus the tail of 9s is 9, and consequently, x equals 1. This is fine, but there are other ways to establish that 0.999999 is actually equal to 1. And it does help to start thinking other ways. For instance, I'm gonna write this down. If they were not different, there would be a gap in between them, in between the two numbers. Yeah, 0.999999. And let's pretend the gap is smaller than 0.0000, just 1, and then a bunch of zeros thereafter. If we add those two numbers, well, we get 9s. Here we get 10, carry 1. 10 again, we carry 1, 10, 1, 10, 1, 10, 1. So we end up with 1 point, a bunch of zeros, and at least 1 9, actually an infinite number of 9s. This is telling us that if you add just about anything, we're going to exceed 1. Okay. Again, if you add any number to this 0.9999, any, no matter how small it is, we will exceed 1. That means that there cannot be a gap between this number and 1. Because if there was, we can add the gap and still be within, we can still be below. So this is another way of thinking of 0.999. We cannot add anything. Because as soon as we add any little speck to it, we will go beyond. Okay, so here we have that 0.99 is equal to 1. Okay, and this is a problem. Then we start becoming very skeptical. Okay, two numbers. No, one number has two representations. What other numbers have two representations? If we want to work with decimals, we better be sure of this answer. Is there any other numbers that have other representations? It turns out that the only numbers that have two representations are the ones that are exact. 0.25 and 0.2499 have two. Well, I'm showing only one here, but any number that ends with zeros, with a tail of zeros, will have two representations. And we can reproduce this proof for any other number. Multiply the number, for instance, in this case, by 100. You end up with 0.999. We just show that 0.999 is equal to 1, so replace it. Replace 0.999 with 1, take it away, take the tail away, and put 1 back in, and you end up with 25, and divide back by 100. So any number such as 0.5799999 is equal to 0.58. But that doesn't tell us that those are the only numbers. We have not seen that those are the only numbers. Yeah. Here's a little proof that shows that those are the only numbers. Let's pretend there's a number that has two representations. And let's call those two representations A and B. And let's assume that the representations are not the same. And let's throw away the 0.99s, by the way, because we already shown that the 0.99 or the 999s, the tails of 9s, can be rounded up. That's another way to think of it. 0.9999 forever can be rounded up to an exact number. So pretend those are two different representations of the same number. Now, what does different representations mean? It means that the digits are at some point not the same, correct? So that could be equal to that. That could be equal to that. But then there's one place where they're different. Otherwise, they're not different. In order for two things to be different, they have to be different at least at one point, in one place. So let's pretend that at this point, the two representations are different. Okay. And now, in a general proof, I would put the ith place. But to keep things simple, let's just pretend that the two numbers, the two representations are different at the third decimal. And let's further assume that this number is bigger than this one. If it isn't, we can always rename the numbers. If this number is bigger, we can just put the number up here and rename it A's, and this number's down here and rename them B's. So without loss of generality, we can do that. I'm not losing you, am I? Okay, so I'm trying to show that two representations cannot give the same number, except the nines, the tails of nines. Okay, the way we're going to show this is by wedging in numbers. That's why I wanted to show this. The two numbers are different if we can show there is a gap in between them. If there's no gap, then they're not different. Yeah. So we're going to build other numbers that are in between. And in the chain of numbers that are in between, there's going to be two of them where there is for sure a gap. So first, I'm going to build C. C is the same thing as A. The only difference is that after this number, the third position, all of the digits are going to be 0. So A is greater than or equal to C. We don't know if they're equal or not, but for sure this number is bigger because we will have more digits up here. Now, we're assuming that B is not doesn't have a tail of nines. If B doesn't have a tail of nines, that means that somewhere we have a number that is not 9, somewhere after this position. That should be the jth position, the position where we don't have a 9. For simplicity of this presentation, we're just going to assume that that place is 6. Yeah. The 6th position is not a 9. What about the other digits? We don't know, but this position does not have a 9. Yeah. We're going to build more numbers above B. Okay, so what did we say? This is not a 9. The most it can be is an 8, because this is one of the elements that is not a 9. And there's got to be 1 because we're assuming there's no 9. There's no tails of 9s. We're throwing away the tails of 9s. So this could be at most 8. All the other numbers could be 9, the most. So this number is above this one, bigger, or equal. Well, let's just say that they could be greater than or equal. Now, this is a tail of 9s, so that we can round this up to the next digit and put zeros. This is an exact number. Yep. And OK. Now, here's where I'm getting a little 9B. What is W? W is, yeah, we're good. Good. W is a number below, a digit below, or one number below A3. A3 was the first digit where the two representations were different. So what I'm establishing here is that this number is smaller than or equal to this one. This one is smaller than or equal to this one. This one is smaller than or equal to this one. And the boxes represent the differences, where the digits are different. Notice that those are a non-strict inequality. So I have not shown any gaps between those numbers. OK, now I'm going to put them all together. There's A, B, and a whole bunch of numbers possibly in between. This line represents that the digits are the same from here to here. Here, there's potential differences. Well, for sure, this number is different than this one. OK, this one is 1 less than A3. This one number is 1 less than A3. So this B3 could be at most W3. This is the most it can be. So this is an upper bound for those numbers. Yeah. This is a lower bound for those numbers. And the difference between the two, same. This is bigger by 1, zeros, and 9. So the difference is 0.000001. I have shown that there is a difference in between the two. Am I making sense, guys? Yeah. Yeah, the difference is 1. I mean, 0.00001. And consequently, that establishes that anytime you have different representations, the infinite representations with decimals, so it doesn't matter if they're infinite or not, but different representations, different decimals, as long as one of them is not nines, a tail of nines, then the other representation is going to be different. We established a gap. In general, the gap would be 10 to the negative j, where j would be the second decimal that is not 9. So, okay, so this is the desired conclusion. Any number d in the interval 0, 1 can be expressed uniquely as an infinite decimal. Now, when I say infinite, I'm throwing away all the exact decimals. So there is no tails of zeros. There's one more thing to do. Well, let me go back to the conclusion. The desired conclusion at this point is that any number d can be represented in this form. Well, we only established that the forms are different. Different forms represent different numbers. Oops. But we did not establish that every number on the interval has a representation. That isn't too difficult to realize because you can always approximate. See, real numbers are actually decimals are very dense, very, very dense. So you can always approximate. You can always have an increasing sequence or a non-decreasing sequence that gets to the point. That does require a little bit of analysis to establish, but intuitively, we can always get as close as possible to any point on the number line with decimals, with infinite decimals. Yep. So the conclusion is any number d in the interval 0, 1 can be expressed uniquely as an infinite decimal. Now, when I say infinite, I'm excluding which ones? Exact ones. I'm excluding exact. Okay. Yeah, and 0 has only an exact representation. 0 cannot be represented with nines. That's why I have to exclude it. Yeah. And any infinite decimal in the above form uniquely expresses a number in the interval 0, 1. What we just did is establish a one-to-one and onto relationship between all the points on the interval from 0 to 1, excluding 0, and the set of all the decimals, infinite decimals. We just did that. We established a one-to-one and onto correspondence between any point here, or all the points here, and infinite decimals of that form. There's a one-to-one and onto. That is a fact. Yeah. Yeah. This was my first attempt. I've been working or thinking of this for a year, just thinking of this. And I thought I got it here with this map. I better go a little faster here. Once you have a decimal representation, you can start working with the decimals. For instance, my first approach was to take D1 and start building X with the odd decimals, the odd place decimals. So the first, the third, the fifth, and so forth. And make Y, or build up Y with the even placed decimals. So the second, the fourth, the sixth, and so forth. That was my first attempt. And I thought I got it. That's why I call it H bar, because later we're going to do a real H. The first attempt, yeah, for example, point 13, 14, 15, no, point 13, 14, 13, 14, and so forth is going to be mapped into 0, 1, 1, 1, 1, 0, 3, 4, 3, 4, 3, 4. Another example, 2, 2, 9, 9, 9, 9 is 2, 9, 9, 2, 9, 9, and then again 2, 9, but the other 9s, which is equal to 0.3 and 0.3, by the way. Okay. Unfortunately, this map is not one-to-one. It doesn't work. Let's see. This number goes to 0.2 and 0.3, comma 0.3. This other number also goes to 0.2 and 0.3. So this map was a failure. This attempt was a failure. But I noticed something, though. The map is onto, because you can always put together any pair by just placing the decimals alternating back in the original number, into the original decimal. So this was good news, even though it is a failure, because where am I here? Yeah, it is onto. Whoa, what happened here? I forgot the parenthesis. Oh, no, I didn't. This map is onto because we can always build if you have any x and y, you can always build a decimal to goes to the pair x, y. I'm just repeating myself. Yeah, the map is onto. This map is not one-to-one, but it is onto. So this is the situation we have. I had a map that was onto, but not one-to-one. Now, when you have a map that is onto, but not one-to-one, that means that there is more elements here than there. As in this case, this is a map that is not one-to-one because x and y are both going to be. Yeah. So that means that I have enough points here to spread over the whole xy plane, or the whole square, because we had a map that is onto, even though it is not one-to-one. OK, so I looked for a map, and I couldn't find it. I spent actually more than 20 hours just on my desk trying to figure this out, and it didn't work. Nothing worked. I was trying to fix it. Every time you're solving a problem like this, it is a roller coaster. You get happy because you think you got it, and then you get sad because you realize that it's wrong. Well, of course, I did Google to see if I could find the answer. And I did find a map. And the way to fix the map is not to alternate decimals, but to take the first decimal for the x, and then any zeros that follow, if any, use those, the next decimal, non-zero decimal, with its zeros that follow, or before it, for the other coordinate. So 2 goes here, 0,3 goes there, 0,04 goes here, 0,05 goes there. There's no 0, so the 6 goes immediately after the 4, and so forth. This map works. I found it in the Nature of Mathematics. There's Dr. Ross has a nice website, and he does some fun stuff in there. And I asked him where he found that, and well, actually, yeah, I asked him. And this is the book where he found it. Now, this happened on Monday, over the weekend, so a copy is coming my way, of course. I ordered a copy of this book. But before that, the only thing that he showed, though, was the map. That's it, with an example. That's the only thing he did. He didn't, and I don't know what the book shows. But in order to conclusively show that we actually have a one-to-one and onto map, we have to be very, very precise. So here is the technical aspects of this. If D is in that set, we can rewrite it with digits, individual digits. That's what this means, individual digits. But we have to take into account zeros in between. Remember back here, there's 0, 0. So I have to take that into account, and then a bunch of zeros. That's what this does. N1 tells us how many places we have to skip before we placing this digit in there. Same thing with this. Maybe there is 3 or 4 zeros to place this one in there, and so forth, each one of the digits. So we have to take into account the digits. For example, 0.907060, etc., is 9 on the first position, 7 on the third position, there's the 7, 6 in the sixth position, 5 on the 10th position, and so forth. Yeah. Now here, if you are taking calculus, you'll notice that you will know this notation, sigma notation. We can rewrite d with sigma notation instead. So all I'm doing is replacing the ellipsis with a sigma notation because we have a pattern. Okay, and here's the actual formula. Remember, in order to establish a one-to-one and onto precisely, we have to have formulas. This is the actual formula. So the x is the sum where the indexes, where we use the odd indexes, 1, 3, 5, and so forth. I could have used a different notation, 2n plus 1 or 2n minus 1. But the formula is not that pretty. It gets a little more messy. But technically speaking, I could have used 2n minus 1 and have a sum that runs over all of the whole numbers. Same thing with this. Yeah. Now, if I want to put this in the x and this next one in the x, I have to take that off, and that's what this means. Take that off, but add the next one. Take the other one off, and then keep adding and subtracting. So this is the correct h. And we can go backward. Remember the example of the 1,000 element? It was 10, 36, and we can go back to from 10, 36 back to 1,000. Similarly here, we have to have formulas that actually take us back. This is the formula. I don't want to spend too much time on the technicalities of this formula, but there it is. There is a formula that will work. If you give me x and y with sigma notations, by the way, each one of the x's and y's represents one digit, only one digit. So this is a precise formula that works. Now, the one thing we established so far, the functions, the formulas established a one-to-one and onto relationship between this set and that set. By the way, composing the formulas requires actually putting one formula inside of the other, and this is what we get just for one x. Yeah. And you can double check the formulas. They do work. Yeah. But so far, what we have is this. We have the set going from 0 to 1 excluding 0, because there is no infinite decimal for 0. And the way we map things, we are also excluding all these zeros here. So this means that we don't have any points on the boundary here, not even the last one. Okay. So we have to, I haven't succeeded yet, because I want to cover everything here, and I want to cover everything there. But the fix is not too hard. Remember, we have composition. Remember L. L mapped 0 into 1/2, half into 3/4, 3/4 into 7/8, and so forth. So L maps 0, 1 closed into 0, 1 semi-open. 0, 1 semi-open, or H maps this set into this set. Now we got to fix this. Okay, and this is the fix. We're going to apply L and H. Then we're going to apply L inverse. L inverse goes from the semi-open set, this is the semi-open set, and we're going to fill in by points. This has to be done an infinite number of times. So what we're doing is, the other way. We're taking this point and mapping it into here to fill in this little gap. But now this is empty, so what do we do with this point? Take 3/4 and map it here, and so forth. And we do that with every point on this line. So this entire line moves here. The line that is at 3/4 moves to 1/2, and so forth. And then we finish the problem by filling this gap. So what we do is we start with something that is not quite right, and then we fix it. That's quite often what I do with math problems. Yeah. And a lot of people do that. We start with solutions that are not perfect yet, but fixable. But they can be fixed. Here's the actual notation. We take composition of functions, starting with L, because composition of functions starts with the right. L, use H, then use L inverse many times. L inverse many times plus 1, and we get the solution. But let's see some examples. Where does 0.77777 go to? There's no zeros in between. And this is not one of those numbers such as 1/2 or 3/4 or 7/8. Those are the only numbers that get affected by L. So this number goes to 0.777, the alternating sevens. This 7, that 7, and alternating sevens. Where does 0 go? Okay, let's look at the picture. It's more fun to see the picture. 0 goes to 1/2. Now 1/2 is the same thing as 0.4999, because we have to put this in infinite, as an infinite decimal. So 49999 goes to 4, 9, 9. And then the other 9s form the y coordinate. So that is the same thing as 0.5 and 1. Okay, so let's look at the picture there. Yep. This point, so where does 0 go? It goes here, and then it goes to 0.51 there. Then it goes to, then it goes to here, to 0, 1. Did I write this down? Yeah, I didn't finish my sequence here. Yeah, it goes to 0, 1. Yeah, let me just double check. Whoops, going the other way. Picture. So this point goes here, that point goes here, and then it fills in this one. And that's it. Yeah, it goes to 0, 1. What about 0.5? 0.5 is equal to 0.800. Now let's see why. 0.5 goes to 0.75. It's one of those numbers that L affects. This number can be written in this way. Then we take alternating numbers. 7, 9, 7, and so forth. 4, 9, 4, 9, 9. This number is 0.8. This number is 0.5. So 0.8, 0.5. Let's see where that went. We are here. 0.8, 0.5. Okay, that does not affect going here, but the 0.5 goes down here. Yep, so we get 0.80. Where does 1 go? Well, 1 goes to 0.999. Well, it is the same thing as 0.999, the same thing. 1 goes to 1, which is the same as that. Take alternating digits, we get this point. And 1, 1 does not get affected by L, or L inverse. Now, going the other way, 0, 0 comes from where? And I don't have the answer. Let's see. 0, 0 came from
0.5.
Yep. That in turn, oh, okay, so we're here now. That comes from here. So now we're here. Now 0.5, 0.5 I gotta write this down. Yeah. 0.5 is the same thing as 0.499, etc., comma, 0.499, etc. And that is the same that comes from putting one number together from those two, 0.44999, etc., which is the same thing as 0.45, and 45 is not affected by L, 0.45. So 0, 0 goes to 0.45, about there. This map is not pretty in the sense that it's not easy to tell where things are going. It does work, but it's not a nice map that works very well. Well, other than the L's, that kind of works sort of nicely. But the H does not work well in the sense that it's not very geometric. It's not very intuitive. It's not like you have to do a computation to figure out where it is going to go. Yeah. It is not possible to have a continuous map from here to there. That is not possible. And this opens up a whole bunch of philosophical questions, too. Is the dimension, if we can do a one-to-one map, what is happening to the dimension? Because that is clearly dimension 2. It's a plane figure, and this is dimensional 1. That doesn't work in this case because we're only looking at the sets as pure sets of points, and that's it. No additional characteristics attached to them. Just sets of points. Clearly, they're not the same kind of mathematical object, though, from a topological point of view, from a geometrical point of view. For instance, and I can quickly give you an example. If you delete one point from this segment, then the set is not connected. You cannot connect it within. If you delete one point from this set, then the set is still connected. You can connect within the set. So they're not, the dimension as a vector space is not the same either. So this establishes a one-to-one and onto relationship between those two sets as sets and only sets. That's it. Any questions?
Are you going to move on to three-dimensional maps from 2 to 3?
No, actually, three-dimensional is actually pretty straightforward once you have this. That's a good question. I'm glad you asked. In 3 dimensions, the only thing you have to do is x, y, x, y, z, x, y, z, x, y, z. And then instead of extending L in only 2 dimensions, where's my picture? Here. So we will have a solid without a face, or a couple faces, but it's kind of easy to fill in the faces in the same way. So 3 dimensions, 4 dimensions, just start alternating digits, non-zero digits, and then you will be OK. Yeah. One of the main things I wanted to show, though, is the formulas. We have to have formulas to clearly and unequivocally show that we have a one-to-one and onto function, precise formulas. Yep.
Alejandro, could you go back to the bijection you showed for n natural numbers and Cartesian product of natural
numbers? There.
Can you explain how you got that formula? Could you explain where that formula came from?
Yes. I used, this took me a while to do. I mean, a while, about 2 hours. How did I do that? You know, in your triangulation, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we know the sum of those is n times n plus 1 over 2. I started with that. And then, let me think. Oh, so that's where the square root comes from, because here there's going to be an n squared. And to be, I cannot reproduce it right now, but that's what I started with, and then I kept adding the positions to this. So there must have been, yeah, there's a subtraction. Oh, okay, here it is. So x is the 1,000, for instance, minus, that number comes from this triangulation. And that tells me the x position. But the formula, I wish I had my notes with me. The formula was a little more complicated than this. I had to tweak it, because this is actually simpler than the formula we are supposed to use. And that took me about half an hour to realize that the tweaking did not hurt, because we're working with integers. So if you perturb the input a little bit, the decimals are not affected. So this formula is actually simpler. I would not dare to be honest, to use the composition of those two. Where is it? To see that we actually get the identity. I think that is too complicated. I would just try to do it in a different way. I know it works, but I didn't actually compose. And why not? Because it was going to take me probably a couple weeks.
Is there another formula besides that one? Is there another formula gives a 1 to 1 and onto?
Yeah, I think, I'm not positive of this, but I'm quite sure we can use the same idea as h, and that would be neater. So instead of going, where is it? Where's my formula? There it is. Instead of dividing by those factors or those tens, multiplying. You can always put a decimals into multiplying, and then it works the other way. I'm guessing. I'm not positive, though. So I would use this formula to establish a 1-to-1 and onto relationship, a precise 1-to-1 and onto relationship. Yep. 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 Any other questions? Well,
Thank you.
thank you. Thank you for coming. Yep.